Thank you for the invitation, Wilson. So I will try to share my screen and see if it works. Do you see it?
Yes, we can see the slides, yes.
Okay, I'll try to put it in full screen. Perfect.
All right.
So just a quick presentation. So I've been leading the human disease vector group of the FAO IAEA Insect Pest Control Laboratory in Austria. And currently I took 1 year of leave without pay to conduct a field trial myself in Réunion Island. And I will try to give you an update on the development of the Sterile Insect Technique against mosquitoes. Although I must say that during the last year, the COVID situation has slowed things quite a lot, especially for the field trials, because many teams have been deviated from their work to help the control of the COVID. But anyway, I will give you an update and try to give you a picture of the current situation. First, I wanted to mention that you are probably all aware that we have 3 major diseases, so dengue, chikungunya, and Zika, that are present worldwide, with an increase of the incidence of dengue that is exponential. And they are all transmitted by Aedes mosquitoes that are difficult to control because they have disseminated small larval habitats that are not easy to treat with conventional mosquito control techniques. And also the adults are biting during the day, so they cannot be controlled easily with mosquito nets. So there is a great challenge in controlling this Aedes species. And that explains why we see an explosion of the number of genetic control methods, including the sterile insect technique. So the sterile insect technique is based on the mass rearing of the target species, the isolation of the males, their irradiation, and their release in the wild environment, so that when they mate with wild females, they transmit sperm containing a large number of random mutations. It's very important to understand that each mosquito that you release will have different random mutations than the others. And so by construction, there is no possibility of evolution of a resistance to this technology. But the problem is that you have to maintain a high ratio of sterile to wild males, because generally it's difficult to get sterile males that will have the same competitiveness than the wild males. And I will come back on that later. The sterile insect technique has been developed against many pest insects. So it includes fruit flies, moths that are pests for agriculture, but also against screwworms that are flies that can destroy a large number of cattle and that were eradicated from Northern and Central America with this technology. And also tsetse flies, and more recently against mosquitoes. And against mosquitoes, we are still at the pre-operational phase in the most advanced countries, and mainly at the pilot phase in most of the countries. So the sterile insect technique can be used in 4 different strategies. The first one is the suppression, to reduce the population under a nuisance threshold. So it's what we do in mosquitoes. We just try to reduce the density of the mosquitoes to avoid the transmission of the disease. It can also be used as a containment technique. So when you know that you have a territory that is neighboring your territory that is infested, you can release sterile males at the border between the 2 territories, and it will protect your area. It can be used as a prevention. If you succeeded to eradicate and you want to avoid that a species reinvade your territory, then you can release sterile males as a prevention. But that's what is done in Panama now to avoid that worms can come back from Southern America to Northern America. And finally, it can be used as eradication. So I was just in Senegal last week to help a tsetse eradication project in Senegal around Dakar. And I think that we are very close to eradication there, because we did not capture any fly since May 2020. So to be able to do that, you must first be able to mass rear your insects. And at the lab in Vienna, we are working a lot on developing methods to make this production cheaper and more cost effective. And I think that I know that in Singapore, you are also doing a lot of progress in this regard, and that we will probably present this progress to the participants. So just to give you some examples of results that we had in our lab, we demonstrated that you can use a powder made of black soldier fly larvae, and you can replace the bovine liver powder with this insect proteins, and you get very good results. So we demonstrated that the quality of the sterile mail that you produce with this method is the same than with bovine liver powder. And black soldier fly powder is more and more available worldwide. It's easier to import it than to import bovine liver powder. And it allows reducing the cost of the diet by more than 80%. So another example is the development of racks. We have been developing racks for decades now at the agency. And here it's a rack that is made of aluminum. And we tried to see if we could reduce the cost using this material instead of inox. And we demonstrated that it can be used. And it allows reducing the cost of the rack by 50%. And if you look at the different units that are used presently, I wanted to show you this table that is extracted from a chapter that is in press in the SIT book. It will be out next month, sorry. And in this table, just to look at something, you can look at the last row, which shows the square meters that are needed to produce 1 million sterile male Aedes albopictus. And you can see that in the first unit, which was the one used by the Wolbachia project in China in the first generation of production, you needed 7.6 square meters to produce 1 million sterile males. And with the one that we developed at IAEA, you just needed 3 square meters. And with the last model that the Wolbachia produced, then you just need 2.3 meters. It's very close to the one that was developed at IAEA, but there is a central wall, and you have 100 trays that are a bit smaller and easier to handle in this Wolbachia unit. And I know that you also have a new automatic rack under development in Singapore. And I hope we will be able to test it and compare it to those racks soon. Another example of research that we are doing now at the IPCL, we received this sex sorter that was also developed by Wolbachia in China. It was developed to sort Aedes albopictus infected with the Wolbachia strain. So it gave very good results with around 0.03% of females contamination in China, but it was with one single strain. So we had one in the lab. It was landed by Wolbachia, and we could test it on another Aedes albopictus strain without Wolbachia, and also against an Aedes aegypti strain. And we succeeded to standardize its use, and we had very good results with a sorting efficiency of 50,000 pupae per hour and female contamination below 0.05%. I know that there is also a robot being developed in Singapore. Another example of evolution that is currently operating, we are trying to develop a more and more efficient mass rearing cage. The model that you see here on the right is not the last model. We just received a new one that is even better. And we succeeded to increase the collection of eggs per initial females, and also to develop a system where there is no more possibility of any escape. So it's very important because it increases the biosecurity in the lab. Because if you have many females escaping, it's a problem for the staff. We also developed a system to use sausages containing much less blood than the previous system. And, I know that in Singapore, you are also using a plate, so you will probably see during the visit if you have any. And now we are using a system where you can put a sausage around, and it also reduces to use the number of to reduce the number of blood by 3. So it's much cost effective, much more cost effective. Another example of a method on which we are working, you may know that in Anopheles, it's impossible to discriminate the males and the females on the basis of the size of the pupae because the two pupae are very close. So we are working on fluorescent strains where we associated a fluorescent protein to the X or the Y chromosome. And so we are using a first strain, the top left here, where only the males are sterile and the females are completely white because the fluorescent protein is on the Y chromosome. So we can extract only the females from this strain. And we have a second strain where the fluorescent gene is on the X chromosome. So the females are twice more fluorescent than the males. And here we can extract the fluorescent males from this second strain. And when you cross the two strains, then you get males that are white and females that are fluorescent, so that you can sort a pure population of males which are white, so that you can irradiate them and release. And this sorting system can be used at the L1 stage of the larvae. So you can sort 20 larvae per second, and you can then put, for example, 18,000 male larvae in a tray and produce only males, which also increase the biosecurity because you will have no female pupae at the end of the process. Of course, at the lab, we are also working a lot on irradiation. So we discovered recently that mosquito pupae are able to use oxygen in the water and at different speed between species. So, for example, Aedes aegypti is able to adapt to the oxygen concentration in its environment. And if you decrease this concentration, it will start to breathe more and more slowly, and it will take up to 40 minutes to use all the oxygen in the water. Whereas if you take a species like Anopheles, it will use all the oxygen in a bit more than 10 minutes. And so it's very important because if the pupae are in this situation, they will be subjected to anoxia or hypoxia. And this anoxia reduces the sensitivity of the pupae to irradiation, but also decreases their quality. So if you put pupae in anoxia for 40 minutes and you look at the flightability, for example, or the competitiveness, it will be reduced even if you don't irradiate. So many programs like the one in China are irradiating very large number of pupae, 30,000 for each irradiation event. And we discovered that it's reducing the quality of the sterile males a lot. And currently we are developing methods to irradiate adults. So we have cassettes containing between 30 and 50,000 adults that can go in the irradiator and then directly in a drone for release. And we saw that we get a much better quality irradiating adults than pupae. Another example of result is that we developed a system that allows marking a large number of adults. So you can mark 50,000 adults in 25 minutes. It's very important because when you start a SIT program, it's important to measure the mortality, the sterility, and the competitiveness of your sterile males. And for all of this, you need to mark your males. So this method is based on chilling the mosquitoes. So as you can see, when they are chilled, you can put 50,000 in a cassette like the one that you see at right bottom of my slide. And you can do it very quickly and homogeneously. We also developed methods for mass transport of sterile males because you have many programs that want to do a pilot project without building a full facility. So to give you an example, Greece started a pilot project 3 years ago, and they are importing their mosquitoes from Italy. And so we developed this system so that you can import your sterile males, and it worked quite well. We had many improvements with the breed trials. And for example, here I will receive all my sterile males from Vienna in Austria, whereas I'm 12,000 kilometers from Vienna to run my pilot trial. We also worked on the release of mosquitoes because currently they are mostly released from the ground. But as you know, Aedes species don't disperse a lot. So if you release sterile males, you will recapture most of them in a ray of less than 100 meters. So it's much more efficient to release them from the air, but it's impossible to release them with planes like for other insects, like for example for fruit flies, because they are much more sensitive. And so we did a trial in Brazil in 2019 already. And we demonstrated that by releasing the sterile males from drones, we obtained more than 50% of sterility in the eggs in the target area and a competitiveness of the sterile males close to 0.3, which means that you need 3 sterile males to compete with 1 wild male and have the same probability that they mate with a wild female. And so we could conclude that the release by drones was efficient because it's very close to what you obtain with ground release. And now we are working on developing smaller drones. And one of them is in Singapore now and is being tested in the field. And this new drone will be less than 900 grams total, including 30,000 mosquitoes. The main limitation to release mosquitoes over urban areas is that the pilot must see the drone, you know, is in his line view permanently. And for this, it means that you cannot release in more than 20 or 30 hectares. So it limits the number of mosquitoes that you can put in the drone because if you need to land your drone every time you treat 30 hectares, then you rarely need to put on board more than 30,000 mosquitoes. We also developed a system to measure the quality of the sterile males. So it's a system that is measuring the flight rate of the mosquitoes. So you can see here a small space at the bottom of these long tubes. And so you put 100 males at the bottom of this system and you give them 2 hours to escape. And they must fly vertically to escape these 20 centimeter tubes. And we could demonstrate that this flight ability is very much correlated with other quality parameters, including mating capacity, and is currently tested in many countries like Brazil, China, and also Singapore. I just wanted to mention that in the literature, many people say that it's impossible to produce an irradiated male that is not competitive and that it's completely false. So I did a review recently, including most of the studies of semi-field trials, so trials in large cages. And as you can see here on the left panel, most, if not all of the studies demonstrated a competitiveness upon 0.2, which is the threshold that is generally considered as cost-effective. So if you succeed to produce sterile males that have a competitiveness more upon 0.2, normally you can run a good field trial. And within the only 4 field trials where competitiveness was calculated recently, which is for Albopictus, Italy on the left, Mauritius in the middle, and China on the right. Of course, in China, it was in combination with IIT. And Egypt only in Brazil is the trial that I just presented with the drone. They were all upon 0.2, which means that it's completely possible to use the sterile insect technique against mosquitoes and that you don't necessarily get males with a lower competitiveness than in other sterile insect programs. I just wanted to mention that this was published 1 year ago, and we currently have 29 trials worldwide testing the SIT against mosquitoes, and 5 more combining it with IIT. And most of these trials are at the preparation stage, but still there are 10 field trials at the pilot stage. And most of these 10 trials are finished now, but the results are not published. Just to give you some examples, in Spain, they succeeded to get more than 97% of suppression during 2 years around Valencia. In Greece, they got more than 95% of suppression. of albopictus as well around Athena. And in Cuba, recently, they got more than 97% of suppression as well. And now they are going to the next step, which is a larger scale and pre-operational phase, where they will look at the impact on the transmission of dengue. So last year, we also issued a guidance document in collaboration with WHO, where you have many aspects of the package that are explained. You know how you have to test the package against Aedes-borne disease, and it's available online. And of course, you can access to it if you want to develop such a program in your country. So thank you very much.